Whoop. Okay, so this is the second problem from the 1.5 practice homework quiz where we're finding the inverse of this piecewise function. Remember, piecewise defined functions, I suggested to first sketch their graph. So for the first piece, which is defined for x less than or equal to 0, the parent function is y equals to the square root of x. And to get this part of this function, from the parent function, there's a vertical reflection and then a horizontal reflection. So the parent function kind of comes out like this, right? Where we have 0, 0, 1, 1, 4, 2, 9, 3, and so on. So there's a vertical reflection, so that's a reflection about the x-axis, and then a horizontal reflection, which would put us into quadrant 3. So the graph for x less than or equal to 0 will have the point 0, 0, negative 1, negative 1, negative 4, negative 2, and we would also, if my graph continued, have the point negative 9, negative 3, negative 16, comma negative 4, and so on. Okay, so that's the first piece of the piecewise function. Then for x strictly greater than 0, the graph will look like y equals to 1 over x. Okay, so that's the point 1, 1. We would have the point 2, comma 1 half, 1 half, comma 2. Okay, so this is the graph of f. And we can see that this graph would pass the horizontal line test. Now what I would do next is to state the y values for which each piece of the piecewise function is defined. So for this first piece, I look at the graph and I see from negative infinity to 0, the y values are defined for this piece of our piecewise function. So that's y less than or equal to 0. Okay, and then for 1 over x, we have y strictly greater than 0. Okay, so notice that these intervals look very similar. So when we find our inverse function, we look to the range of each piece of the piecewise, because that's now going to be the domain restrictions for inside the piecewise function. But because these are actually kind of the same intervals, when we flip-flop the x and the y's, those inequalities look the same. So we're actually going to have the same domain restrictions on each piece of the piecewise for the inverse function, and we can already see that. Now let's also state the domain and the range for our function f. So the domain, we read the graph from left to right, is going to be all real numbers. And the range, as we read the graph from bottom to top, will also be all real numbers. So now we can also see that for f inverse, okay, we don't even know what that equation looks like yet, but from f inverse we can see that the domain and the range will also be all real numbers. Now, before we even find this equation, since we know points that lie on f, we actually technically know what the graph of f inverse would look like. Because remember, the x and the y values switch. So for example, we have the point negative 4, negative 2 on the graph of f, which means on the graph of f inverse, we would have the point negative 2, negative 4. Okay, we have the point negative 1, negative 1 on the graph of f. If those two values switch, it's still at the point negative 1, negative 1. 0, 0, those x and y switch, we would still have that point. 1, 1, we would still have that point. If we switch, so we have 2, comma 1 half, well, that's the same as 1 half, comma 2. So we can kind of see what f inverse is actually going to end up looking like without even needing to know what the actual equation is. And I'll show you after we find the equation that it matches up with this purple graph. Okay, So that's something that I haven't shown you before, but that you should be able to kind of extend and know from your knowledge of inverse functions. So let's find the inverse of this first piece. So remember, we switched the x and the y. Okay, and now we are solving for y. So I would divide each side or multiply each side of the equation by a -1. Okay, now because I'm trying to get the y isolated on the right hand side, I'm going to square both sides. And then to finish getting y by itself, I will divide by a -1 on each side again. Now remember, this negative happening to where we have -1 being multiplied by x, that represents a horizontal reflection, which for x squared, that doesn't make a difference with the graph. So this could actually be just written as -x squared. Okay, those two graphs are going to look equivalent because the horizontal reflection to the graph of x squared, it's not going to change the graph. Okay, and this is going to be for, I look to the y interval up here. So this is going to be for x less than or equal to 0. Okay, next piece. If I have y equals to 1 over x, we multiply both sides of the equation by x to get xy equal to 1. Well, now if we divide by, oh, I screwed that up. Sorry. So if I have x equal to 1 over y, sorry, I forgot to flip the x and the y right there. But I multiply by y on both sides of the equation where I have yx equals to 1. And then I divide by x on each side to isolate the y. Well, guess what? I still end up with y equals to 1 over x. Okay, and you could see where each of the points that are on 1 over x, they are reflections about the line y equals to x. Like you could see on the purple part when I was trying to flip the x and the y value, well then I just ended up with this point up here. This point became this point down here on f inverse. Okay, so the graph of f inverse will look like 1 over x for x strictly greater than 0. So putting that information together, f inverse is -x squared for x less than or equal to 0, and 1 over x for x strictly greater than 0. Where the domain is all real numbers, the range is all real numbers. Okay, and I know that from the domain and range of the function f. So then just confirming our graph of f inverse with the graph that we plotted before we even knew the equation for f inverse. For x less than or equal to 0, the graph will look like y equals to -x squared. Well, the parent function here is x squared, okay? And then if we have a vertical reflection, that would be x squared, but it's been reflected about the x-axis and it opens downward, but it's only for x less than or equal to 0. So we have the point 0, 0, -1, -1, -2, -4. We would have -3, -9, and so on. Okay, and then for x strictly greater than 0, we know what 1 over x looks like, so that just overlaps. And then just kind of our final piece of proof is if we sketch the line y equals to x, okay, we can see that if we were to reflect the graph of f about this line, it would match up with the graph of f inverse. Or if we were to reflect, okay, so flip the graph of f inverse about the line y equals to x, it would match up with the graph of our function f. Okay, I hope this helps. Let me know if you have any other questions. Send me an email this weekend. Good luck.